Hi. We have been examining the application for using application of the usage of the complex power. So the first application was related compensation. So let me go into that frame. We have examined that compensation. Now we will be examining the line efficiency. Line efficiency, let's go in. So this is the energy source and this is the equipment that we are using. The energy originated place and the energy usage place are far away from each other. So that means you can consider this one as cabin, and this may be any appliance in your house. So in between, what we've got a line. This is called electric line. So our aim is, normally engineering, if you consider the engineering side of it, we would like to lose minimum number of energy on that line. That means maximum power should be transferred from source to my load. Whatever lost in between is the lost. So that means there is no use for this power. It has been lost for transferring the electrical power from one point to another. So now we would like to find out the efficiency of this line. That means the power we consume here over the power originated from the origin. So that means how much of them has been lost in the line. So efficiency is the average power being consumed in here over the total power getting out of the source. So in order to do that, we are going to do to see the details. I will be transferring to open board. Now open board, here we are. So I will be using a complex power calculation, a special formula for this application. We know that complex power N is equal 1 over 2 V times I complex conjugate of I. So this is the current of this impedance. That's the voltage of this impedance. The complex power of this impedance is equal to this one. The average power is going to be the real part. Reactive part of it is going to be the imaginary part of this complex calculation. So if then I can write 1 over 2 V is the phasor of the voltage of this impedance. So this is equal Z time I. So what I have done, use the definition relation of the Z impedance. So multiplied with I conjugate. So that is V. So this is equal 1 over 2 I effective value of that current square of it. So multiplied with Z. Then if I take real part of it, real here, it will be the P average. So if I apply it to this load now, it's going to be, so if you apply it in here, so it's going to be the P average for this Z impedance is equal 1 over 2 E effective square real part of the Z, because this is real number. We know this is the, what is the effective? E effective is E max over square root of 2. So this is a positive real number. This is not a complex number. So the square of it is a real number. So to get the real of these formula, we are going to get the real part of Z. Real part of Z is X. So the average power is going to be equal to this. So I will be using this formula in order to find out the efficiency of this line. How I'm going to apply it? Easy. I'm going to find out the average power of this load. P average for this load is equal 1 over 2 I effective square times 4, isn't it? X, which is equal 4. This is impedance, real part of it. That was X, real part of my impedance. That is 4. Now, if you examine this circuit now, this circuit has got one loop here. So that means there's the current passing through all these elements. They are equal to each other because they are all connected in serial. Therefore, the effective square for all these elements are going to be the same. So P average, that is load, for the load, that is total average power getting out of this. The total one is going to be summation of those two. So total impedance, real part, is 1 plus 4. So total 1 over 2 E effective square, X is 5, isn't it? Total 1 ohm plus 4 ohm, that gives you that. Why it is total? That is the total impedance, isn't it? Total impedance real part is this. My load impedance real part is this. So this division of those two is going to give me efficiency. Is equal. Since these currents are equal, because all these elements are connected in serial, current maximum value of the current, they are going to be all the same. So this efficiency is 4 over 5, that is 80%. Meaning is this: the power you originated here, 80% of that power has been sent to this load. The rest of the 20% of my power has been consumed by this line. So that's why this gives the efficiency, and 20% of the electrical energy has been lost on that line. So that is lost, isn't it? Lost energy. So this is the line efficiency. So that's the end of this video then. And I can say, let me this one and get this one.